Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and the motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we focus on one essential component of the epistemic firewall. In this part 18, we address the fundamental act of discovery, inferring rules from many sentences, hearing invariance across many windows. This is the firewall mechanism that governs how we move from scattered, noisy observations of phi to a confident claim about a universal constraint. The skill you will gain is that of a data counselor, the ability to assemble, evaluate, and synthesize an ensemble of phi sentences to distinguish a true pattern of law from a mere coincidence or local artifact. Our core question is, how do we move from single events, sentences, to constraints, grammar? This question targets the heart of induction. A single phi sentence, a measurement within one window W with uncertainty delta, is a point of data. It is not a law. It is a single note. A law is a constraint, a grammar that predicts the relationships between notes. We infer a law when we perceive the same triunity structure repeating across many independent licensed windows. The firewall's inference function demands this repetition. It requires that any proposed rule demonstrate its invariance, its persistent echo, across a disciplined diversity of observations. A rule that only appears in one type of window, under one set of conditions, is a candidate hypothesis, not a licensed law. The core revelation is, a law is invariant relationship, not a single relationship. Truth is not in a single perfect measurement. It is in the consistent pattern that emerges despite variations in measurement context, scale, and perspective. The signal of law is stability under variation. Let's build this from the ground up. Recall a phi sentence. It is a data structure, a tuple of numbers extracted from a window W with an associated uncertainty delta. Let's denote the ith sentence as S sub I. It contains information about phi's behavior in a specific region of omega k and v. For example, in studying a pendulum. Sentence S1, period t equals 2.005 seconds, length L equals 1.000 meter, amplitude theta equals 5 degrees. Uncertainty delta on t is plus minus 0.001 seconds. Sentence S2, period t equals 2.838 seconds, length L equals 2.000 meters, amplitude theta equals 5 degrees. Uncertainty delta on t is plus minus 0.001 seconds. Sentence S3, period t equals 2.010 seconds, length L equals 1.010 meters, amplitude theta equals 15 degrees. Uncertainty delta on t is plus minus 0.002 seconds. Each sentence is a local fact. The rule, the grammar, is the constraint that relates these sentences. For a simple pendulum, the proposed rule G is: the period t is proportional to the square root of the length L. In symbolic form, t equals 2 pi times square root L over G, where G is a constant. Spoken. T equals 2 pi times the square root of L divided by G. But how do we infer this rule G from the sentences S1, S2, S3? We do not just look at one sentence. We look for the invariant relationship that holds across them. We formalize this with an audio equation. Let's define the process. We have a collection of n phi sentences, S1, S2, Sn. Each sentence Si can be thought of as a point in a high-dimensional space of measured quantities. For the pendulum, that space has axes, period t, length L, amplitude theta. We also have a candidate rule G from a registered model class M. Rule G makes a prediction. For the pendulum rule, it predicts that the quantity Q equals T by square root of L should be constant, equal to 2 pi slash square root of G for all sentences where the amplitude is small. So for each sentence Si, we compute the derived quantity Qi equals Ti by square root of Li. Now the inference test. Do the values Q1, Q2, Qn, each with their propagated uncertainties delta Qi, cluster around a single constant value C? We assess this by calculating the weighted mean and the reduced chi-squared statistic. Let's walk through this audibly. First, the weighted mean Cest, estimated constant, is calculated by giving more weight to sentences with smaller uncertainty. Cest equals sum over I of Qi by delta Qi squared by the sum over I of 1 by delta Qi squared. Spoken. Cestimate equals the sum of each Qi divided by its delta Qi squared, all divided by the sum of 1 over each delta Qi squared. This estimates the central invariant value the rule predicts. Second, we calculate how well the data cluster around this estimate using chi-squared. Sum over I of Qi minus Cest squared over delta Qi squared. Chi-squared equals the sum over I of the square difference between Qi and C-estimate divided by delta Qi squared. If the rule is true and our uncertainty estimates delta Q are correct, we expect chi-squared to be roughly equal to the number of sentences n, or more precisely, the degrees of freedom n-1. If chi-squared is much larger than n, the Qi values are too scattered. They are not invariant. The rule fails. If chi-squared is much smaller than n, it often means our uncertainty estimates delta Q are too large. We were overly cautious. The inference of a rule is the assertion of this invariance. We claim, across all these varied sentences, different lengths, slightly different amplitudes, the derived quantity Q remains constant within expected noise. The rule G is the expression of that constant relationship. T by the square root of L equals constant. Now, why is this multi-sentence approach necessary? The failure mode it prevents is generalizing from a single instance or a biased sample. A single sentence, no matter how precise, can be a fluke, an artifact of your apparatus, or a special case. Only by checking that the proposed relationship holds across a disciplined ensemble of windows can you begin to claim it is a constraint of phi, not a coincidence. The firewall's inference gate, therefore, is the data council. To propose a rule, you must present not one sentence, but a curated ensemble. This ensemble must demonstrate 1. Diversity. The Windows W must vary in their omega, k, and v parameters. For example, different times of day, different spatial locations, different velocities of the apparatus. 2. Independence. The sentences should be derived from independent data pipelines where possible to avoid correlated systematic errors. 3. Declared uncertainty. Every sentence must come with a rigorously estimated uncertainty delta. 4. Scope coverage. The ensemble should probe the proposed scope L of the rule. If the rule claims to work for small amplitudes, the ensemble must include sentences at various small amplitudes. This council reviews the ensemble. It asks, does the invariance hold? Or does the derived quantity Q drift? Let's integrate this with the triunity. This is where the power of the method becomes clear. We are not just looking for any invariance. We are looking for the repetition of triunity structure. When analyzing sentences to infer a rule, we must look for the repeated coupling of omega k relationships. Does a specific temporal rhythm, omega, consistently associate with a specific spatial structure, k? In the pendulum, the period, omega type, is tied to the length, a k-type geometric property. K-V relationships. Does a spatial structure consistently dictate a type of motion or flow, V? In fluid dynamics, the shape of a pipe, K, determines the flow profile, V. Omega V relationships. Does a temporal rate predict a kinematic behavior? In radioactive decay, the decay constant, omega type, dictates the rate of particle emission, V type. Most importantly, we seek the triple lock, the consistent joint relationship of omega, k, and v together. A real law binds the three echoes in a fixed dance across all windows. When you change k, the omega-v relationship changes in a predictable way prescribed by the rule. For example, in wave propagation. The rule is the dispersion relation. Omega equals c times k, where c is v, the propagation speed. Spoken. Omega equals c times the magnitude of k. We infer this rule by collecting sentences, wave measurements, at different frequencies, omega, and measuring their wavelengths, related to k. We check if the ratio omega/k is invariant, equal to c, across all these diverse sentences. The triple lock is the constant coupling between the temporal frequency, the spatial wave number, and the propagation speed. Now, connect this to energy as tally. This provides a powerful litmus test. When the inferred grammar is real, the energy tallies computed from the sentences stabilize across windows within their uncertainties. When the grammar is fake or incomplete, the energy tallies drift with context. Energy is a derived bookkeeping quantity. For the pendulum, the total mechanical energy tally is E equals half mv squared plus mgl, 1 minus cos theta. E equals 1 half mv squared plus mgl times 1 minus cosine theta. If our rule, the equations of motion, is correct, and we have accounted for all relevant omega k or v relationships, like damping, then the energy E computed from sentences at different points in the swing should be constant, invariant. If we have the wrong rule, if we've missed a force, the computed energy will not be invariant. It will appear to increase or decrease across sentences. Thus, the invariance or non-invariance of the energy tally across a multi-sentence ensemble is a direct test of the grammatical inference. Energy conservation is not an independent principle. It is a consequence of inferring the correct invariant triunity relations from the data. The operational interpretation is the daily practice of statistical model fitting and hypothesis testing in experimental science. Scientists collect many data points, sentences, plot them, fit a curve, the rule, and compute residuals and goodness of fit metrics, like chi-square. They vary experimental conditions to test the rule's robustness. They use independent labs for application. This entire process is the operationalization of multi-sentence inference. The firewall role is that of the data council gate. You are the counselor. When a researcher presents a rule G inferred from data, you demand the ensemble. You ask, show me the full set of phi sentences their uncertainties, and their diversity in omega, k, and v space. Show me the invariance plot. Show me the chi-square. Show me the analysis of energy tallies across the ensemble. You are verifying that the leap from data to law is justified by breadth and consistency, not by a single lucky alignment. Let's state clearly what is allowed and forbidden. Allowed. You may infer a rule from a relatively small ensemble if the uncertainties are small and the invariance is spectacularly precise. You may also propose rules with a scope LA that explicitly limits them to certain omega k v regimes. The rule's license will then be scoped accordingly. Forbidden. You may not proclaim a rule based on a single phi sentence or a handful of nearly identical sentences. Hide sentences that contradict the invariance, cherry picking. Use an ensemble that lacks diversity in all three echoes, omega, k, v. Ignore or underestimate uncertainties delta to make scatter appear smaller. Claim a rule is universal when the inference ensemble only covers a narrow slice of parameter space. What happens when the check fails? The license consequence is direct. Fail, no certification. At best, a local hypothesis with explicit scope restrictions and increased uncertainty. The rule is not granted a broad license. It may be labeled as a working model valid for conditions X, Y, Z, with a note that its inferred parameters have high uncertainty due to poor ensemble quality. It cannot form the foundation for further theory without a stronger inductive basis. Now, we must state the explicit prediction and falsification for the inference process. Prediction. If a rule is real, a true constraint on phi, then as we add more independent, diverse phi sentences to our inference ensemble, the uncertainty on the inferred rules parameters will shrink predictably, like 1 over square root of n. And the inferred omega per k per vi relationship will become sharper and more stable. The central estimate, Cest, will converge, and the chi-squared per degree of freedom will tend toward 1. This is the prediction of convergent invariance. Falsification condition for the inference. If the rule changes unpredictably as new within-scope windows are added, if the derived quantity Q shows systematic drift or the best fit parameters shift beyond their estimated uncertainties, the inference collapses. The falsification is the breakdown of invariance. The rule is not a stable grammar. It is a local approximation that fails to generalize. Adding sentences should refine a rule, not redefine it. A classic historical example is the inference of Newton's law of universal gravitation. It was not inferred from one observation of the moon. It was inferred from a multi-sentence ensemble. Kepler's laws of planetary motion. Many sentences about different planets' periods and orbital radii, combined with data on falling apples, the tides, and the precession of pendulums at different latitudes. The invariant quantity was the proportionality between the gravitational force and the product of masses divided by distance squared. This relationship held across a stunningly diverse ensemble of omega k by v contexts, celestial orbits, terrestrial falls. Its power was in its invariance across that ensemble. When later sentences, the precession of Mercury's orbit, showed a small but persistent break in the invariance, it signaled the need for a new grammar, general relativity. Now let's explore an Afghanistan-inspired analogy that roots this abstract process in tangible community wisdom. The collective diagnosis of a failing Karez irrigation system. A single farmer comes and says, "My field is dry, the Karez is broken." This is a single phi sentence. It is data. Location, field A. Condition, dry. Time, now. From this alone, you cannot infer the rule of the failure. To diagnose the systemic rule, the constraint causing the failure, the village council must assemble a multi-sentence ensemble. They gather reports. Sentence S1. Farmer A. Field dry, outlet A1 dry, upstream section. Sentence S2. Farmer B. Field damp but not flowing, outlet B2 weak flow, midstream section. Sentence S3. Farmer C. Field completely flooded, outlet C3 gushing, downstream section. Sentence S4. Sentinel at Motherwell, water level normal, source. Each sentence is a local window W into the state of the phi system, the water flow in the Carrez. Each has uncertainty. For example, weak flow is a qualitative delta. The council now looks for invariant relationships, the grammar of the failure. They test hypotheses, candidate rules G. Rule G1, blockage. There is a single blockage. Upstream of it, dry. Downstream of it, flooded. This predicts a specific spatial pattern, K, linking the sentences. Rule G2, general siltation. The entire tunnel is silted. Flow is reduced everywhere. This predicts uniformly weak flow at all sentences, which contradicts S3, flooding. Rule G3, structural collapse. A tunnel section has collapsed, diverting water to a surface crack. This predicts a loss of water between the mother well and outlet A1 with possible surface seepage. To infer the correct rule, the council needs more than one sentence. They need the ensemble. The pattern in the ensemble, dry upstream, flooded downstream, normal source, is invariant to the specific farmers. It points to a specific structural constraint. The invariant is the discontinuity in water presence along the spatial coordinate. This tightly fits rule G1, blockage, or G3, collapse. Further sentences, for example, inspecting the tunnel between A1 and C3, will refine the inference. The energy tally in this analogy might be the total water volume per day. If the inferred rule, for example, blockage at point X, is correct, then the calculated water budget, inflow from mother well equals outflow past blockage plus seepage loss, should be invariant, balance, across time windows. If the rule is wrong, the tally won't balance. The council acts as the firewall's data council gate. They reject a diagnosis based on one farmer's report, a single sentence overgeneralization. They demand the ensemble. They look for the invariant failure pattern across multiple independent windows into the system. Only then do they authorize a costly repair, the experimental test of the rule by digging at the inferred blockage point. This communal, multi-perspective inference is how complex distributed systems are understood and managed. It is the essence of inductive reasoning made robust. In Holophase science, the failing Carrez is the universe with an unexplained phenomenon. The farmer's reports are our phi sentences from telescopes, particle colliders, and lab benches. The village council is the scientific community. The inference of the failure's rule is our proposed physical law. Without the disciplined ensemble, we are just a single farmer shouting into the wind, mistaking a local problem for the nature of the whole system. Now we state the mandatory Ep.11 axioms, now embodied in the inference process. Rules do not become real by elegance, consensus, or tradition. They earn a license only by surviving falsification, variation, independence, and scope discipline. Multi-sentence inference is the embodiment of variation and independence. The rule is tested across varied windows, variation, and ideally independent instruments, independence. Its inferred scope L is directly determined by the range of omega per k by v covered by the ensemble. The very act of demanding an ensemble for inference builds these axioms into the rule's birth. And when a rule fails, we do not believe harder. We tighten, downgrade, or retire its license. In inference, failure is the breakdown of invariance when new sentences are added. The response is to tighten the rule's scope to the domain where invariance still holds, or to downgrade its status to a mere empirical fit. The skill you gain from this part is inductive rigor. You learn to be deeply skeptical of any claim that leaps from a single experiment or observation to a grand law. You demand the ensemble. You look at the scatter plots, the residuals, the goodness of fit. You ask, over what range of conditions has this invariance been demonstrated? This skill protects you from the seduction of dramatic but fragile discoveries. This has immediate, vital application in clinical trials. A drug's efficacy is not inferred from one patient. It requires a large, diverse ensemble of patient sentences, randomized controlled trial, to infer the true rule of its effect. Climate science. The inference of anthropogenic climate change is not from one hot year. It is from a vast, global, multi-sentence ensemble of temperature records, ice cores, sea level measurements, and model comparisons, showing an invariant trend linked to CO2 levels. Particle physics. The discovery of the Higgs boson was not a single event. It was an invariant signal access persisting across millions of collision events, sentences, in two independent detectors, ATLAS and CMS, across a range of energy channels. Finally, let's summarize the epistemic function of this part. We have defined the process of inferring rules from many sentences as the firewall mechanism that moves from local data to candidate laws by demanding the demonstration of invariance across a diverse ensemble of 5 sentences. This process explicitly tests for the repeated triunity structure, omega KV relationships, and uses the stability of derived tallies like energy as a key diagnostic. The firewall acts as a data council gate, requiring the presentation of a disciplined, diverse, and uncertainty-quantified ensemble for any inductive claim. The explicit prediction is convergent invariance. More and diverse sentences will sharpen and stabilize the inferred rules parameters. The explicit falsification condition is the breakdown of invariance. The rule's core relationships change unpredictably as new data is added. The license consequence is withholding of certification for rules inferred from weak or non-diverse ensembles, limiting them to narrow, explicit scopes. This strengthens the firewall by grounding the very act of discovery in a rigorous, multi-point check. It ensures that rules entering the licensing pipeline have already passed the first great hurdle. They are not mere anecdotes, but patterns that have demonstrated their persistence across a range of reality's whispers. It is the difference between hearing a voice and understanding a language. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Carry the discipline of the data counselor. In a world of infinite data points, be the one who demands the ensemble that reveals the pattern. This is how we learn to listen to reality's grammar. Now we bridge to the final, crucial challenge in our epistemic architecture. Many rules can fit the same collection. How do we choose without ideology? This leads us to the ultimate arbiter, the engine of selection under uncertainty. Salam and peace be upon you.